Oh, let me see. Let's try this again. There we go. Okay. Welcome to lecture 27. How did the calculus-based homework go? Is it okay? By the way, and we are actually going to use the result from that homework today. I have here a right triangle here drawn on the board with side, like width b and height h. If this is the location of the centroid and this dimension is b, what's that dimension?
1/3
b over 3. And if this dimension's h, what's this dimension? H over 3. Okay, we are going to use that today. All right. The purpose of that assignment and what we did in class on yesterday is to lead directly into what we discussed today. Okay, and most of the time, what you're going to be doing in practice as engineers is not deriving using calculus centroids of fundamental shapes. What you are going to be doing is computing the location of centroids of composite shapes. Okay? In other words, if I have a plate with a bunch of holes in it and a triangular component, how do I compute the centroid of that? Well, I break it up into simple shapes, like a rectangle, like a triangle, like a circle, and what have you. And so if you understand how to locate the centroid of these simple shapes, you can get a lot done with no calculus. And whenever you hear no calculus, most engineers' day it just gets a lot brighter when they hear no calculus. That was a joke, not a funny one. Okay, I'm still working on grading the exam, probably next week, something like that. I think all the outstanding homework, though, is graded. So, sound good? All right, so let's go ahead and jump into it. Let me close this. Close it. I was loading up an instance of Adobe, and you'll see why here in a second. Okay, so last time we sort of did this, okay? And what we did last time is we said, okay, we can locate 2 points. So there's a lot of equations baked here on this slide, but it's really all saying kind of the same thing. We can locate either the center of gravity or the centroid by treating a shape as sort of an equivalent system, okay? The center of gravity is referencing a location in terms of weight, whereas a centroid is referencing a location in terms of its geometry. So we're taking the specific material out of it, the specific thickness, and so on and so forth, which for most applications is perfectly fine when you have components all made of the same material and so on and so forth. We can express centroids either from a calculus-based perspective or an algebra-based perspective. And so if you're deriving the location of the centroid of a fundamental shape, or if your geometry is particularly rough, you do kind of need to use the calculus-based formulation in order to locate it. But often in engineering, we are dealing with composite shapes. And so we can actually compute the location of the centroid just using a weighted average approach like you see here. And that's what we're going to do today. So let's talk about practical real-world centroid problems. So if I gave you a shape like this, okay, I would not expect you to start breaking out equations and integrals to locate that centroid. I would just expect you to use previously derived formulas, okay? If we look at this shape, I could break this shape down into one rectangle and 2 triangles. So just use a weighted average approach and use our summation formulas directly, okay? And by the way, I might show you this a little bit later, but you can actually use AutoCAD to locate a centroid. You can draw a shape and use the mass properties command, and it'll just locate the centroid for you. I might show you that a little later. Bless you. Now, one of the downsides of this method is that you do kind of need those pre-derived formulas. Like if you're going to use the centroid of a rectangle, centroid of a triangle, if you're going to use these, you kind of need to know what those properties are in advance. Now, if you have what I would call some really out there shapes, I don't expect you to memorize all these. You can look them up. There are some of them, though, that I would expect that as engineers you do kind of need to know. I'm not one to expect that students memorize these. I'm not a memorization guy. I think that you should be able to find the information and utilize it. That being said, I don't know many practicing engineers that couldn't tell you that the centroid of a right triangle is a third over from the right angle on either end. Okay, that's just one of those numbers. I'm telling you, for the next 3 years in college, you are going to be using this pretty much every semester. Okay, and if you have to look it up every time it comes up, you're going to put yourself at a disadvantage. The two centroid formulas that I think you should probably, I don't want to say memorize, but at least have jotted down, is this one and this one. Okay, so if you have a semicircular region, where is the centroid? Okay, well, the centroid is symmetric about the center line, and then as for where it is up and down, so if you go from the flat end up, the distance is 4r over 3 pi. Okay, that's where the centroid is, and you can derive that if you want, but again, we're more about, now that we understand the derivation process, I want you using them. Okay, now I don't expect you to memorize where the centroid of a quarter elliptical area or a parabolic region. I don't expect that. And to be honest, we're really not going to use them very much. And I don't know many engineers that use them very much in a lot of practical settings. Maybe there are some specific applications, but I personally don't use them very much. I can do a lot of damage with just triangles, circles, and this. If you need some more out there centroid locations, for one, your textbook is going to have these things. The other thing I wanted to point out is the NCEES reference manual. Do you all know what I'm talking about when I say the NCEES reference manual? How many of you have heard of the FE exam? When you take the FE exam, you are allowed a calculator, a little notepad to write on, and this, okay? This is, by the way, I think everybody should just have a copy of this downloaded because there's a lot of really good stuff in here. This is the reference manual that you get during the taking of the FE exam. There's a lot of really good stuff in here. Just like, you know, like all the derivative formulas, integral formulas, and there's just a lot of really good stuff in here. But if you go down here, let me see. Let me find it. Or maybe I'll just go to this right here. Let's go to statics. Oh, look, it's all this stuff we talked about all semester. It's crazy, isn't it? So, let's see. If you go here into the, for example, centroid reference, you can see, like, for example, here's a rectangle, and here's where the location of the centroid is. Here's the triangle, here's where the location of the centroid is. And, for example, if you go to the semicircular region right here, you can see that here's a semicircle, here's the location of the centroid. They call it A here, 4A over 3 pi. So this is a very valuable guide, independent of everything that we're doing in Engineering 213. I would download a copy because it's pretty useful. One thing I will tell you, since I'm sure this question is going to come up for exam 3, if you need any specific centroid formulas, I will give them to you on the exam. What I'm not going to have you do is waste space on your formula sheet putting stuff that, in my opinion, is just reference lookup stuff anyways. Does that make sense? I'm not going to make you do that yet.
Up there on that semicircle thing, so what does that say? Symmetric about what?
So, oh, you don't recognize that as the center line symbol?
I just gotta read what it said.
Oh, sorry. That's the center line, sorry. So, remember this symbol in Engineering 102? It's the center line. So I'm saying this is symmetric about the center line. Sorry. I did just sort of gloss over that, didn't I? But yeah, that's just my shorthand for the center line. Okay. All right, don't worry, we'll practice using these here in a second. Okay, whenever you're computing centroids, you are going to be using a weighted average, and so I want to make sure that you're doing it properly. So I've got two items that, I mean, I've been teaching this for a while, and these are the things that I've noticed that are problems whenever you're doing these types of calculations, maybe on homework or an exam. Okay, so whenever you're computing the location of the centroid, make sure that you're taking care to appreciate your signs. So whenever you're calculating, for example, holes are going to be treated as negative areas, okay? And whenever you are calculating locations, respect the coordinate system. So, like for example, let's say I was computing the location of the centroid of this shape, okay? So I've got three regions. We'll call it this semicircular region, this rectangle, and this hole, okay? So if I was thinking about the area terms, so let's say I'm trying to find x bar, the centroid this way, okay? So for the areas, A1 is positive, A2 is positive, and A3 is going to be negative because it's a hole. I'm removing that area from the shaded region. Make sense? But then when I'm trying to define the centroidal distances, like the x distances, x2 is going to be positive, x3 is going to be positive, but x1 is going to be negative. Okay? Because the idea is I'm saying, okay, here's my shape, and I'm saying this is my coordinate system. There's the origin. That's my reference from where I'm referencing all the distances. And the x distance is going to the left. Does that make sense? So if I were to write this out, let's say in a table for the semicircle, it's a negative distance, positive area. For the rectangle, positive distance, positive area. For the circular hole, positive distance, negative area. And so ultimately, what we're going to be computing is the sum of x times a over the sum of areas. So again, like if this is negative and this is positive, that product is negative. If this is positive and that's negative, that product is negative. Does that make sense? So respect the signs whenever you're doing this. Okay, that's point one. The other point I would mention is that centroids exhibit or respect a shape's symmetry. Okay, so I don't care what the shape looks like. If it has any axis of symmetry, the centroid is on that axis. Okay, so for example, if I'm looking at this trapezoid, like here's the trapezoid, we could have an argument as to where the centroid is measured up and down, but left and right, it's right here, okay? It's right there. Because, so here's the reason why. So if like we look at this shape and we take like just some element, we have an area times negative x and then an area times positive x. And so for every element of area, it is going to be multiplied both by a negative x and a positive x. And so if you were to calculate the centroid, you'd have some sum of area, but this would ultimately go to 0. Okay? Does that make sense? Everybody okay with that? All right. The other thing is the centroid does not have to be on the shape. Again, last time we talked about Homer Simpson and the donut. If you had a donut, if we had a big, chocolate donut. We had a chocolate donut. Where would the centroid on that donut be? In the middle, right? Here's my wedding ring. Where's the centroid? It's in the ring. It's in the hole of the ring, right? Does that make sense? So it doesn't have to be on the shape. So if you're computing the location of the centroid and it's not on the shape, that's not necessarily an error, okay? Don't think that's anything wrong. Sound good? Okay, so I want to spend today's lecture going through this example, okay? So we're going to determine the location of the centroid with respect to the coordinate system shown. So whenever you do a centroid problem, you have to, here's the shape, you have to pick a coordinate system. Because ultimately what we're going to do is I'm going to say, okay, where is the centroid? And I'm going to say, there. Okay, where is there? Well, it's got coordinates. Coordinates from what origin? So you have to pick a coordinate system and go with it. So we're going to use this coordinate system, and we're going to do it like this. Okay? Now, I'm going to show you a way to do this problem. We're going to do it that way, and then I'm going to show you another way. See, here's the thing. There's multiple ways to split this shape up, and any one of those ways will yield the same answer. That is probably not all that clear right now, but when we do the problem, you'll see what I mean. So, okay. make this a little bigger. Okay, so here's the shape, and we're going to, so first off, all the distances are in millimeters, so I'm going to be a little light on in terms of the units in my tabular computations. I'll just put the units on the top and just go with it. What we're going to do is we're going to divide this up into a series of simple shapes. Okay, and I'm going to show you what I'm going to do. So, okay, so I don't know how we want to head this. We'll head this, maybe call it discretization. Okay. What's that?
What's that mean?
Means split it up into little pieces. Discretize. I so rarely get to use that word in a sentence. Okay, so here's what we're going to do. All right, so here's the coordinate system. And give me a little bit of rope here. Bear with me because I want to explain what we're going to do. Okay. So what we're going to do is we're going to split this up into the following region. Up. So I'm sure some of you are like, what is he doing? Just bear with me. Okay, so what I'm going to do is let's label this 1. We'll call this 2 and 3. Okay. So what I'm going to do is I'm going to take this shape, I'm going to split it up into the following 3 regions, and I'm going to treat these as positive areas. Okay? So I'm going to have this semicircle, I'm going to have a rectangle, and then I'm going to have a triangle. And then what I'm going to do is this. Okay? What I'm going to do is from this, I'm going to subtract the following. Okay, so the idea is that I'm going to treat this as a positive area, this is a positive area, and this is a positive area, and this is a negative area, right? So the idea is if I took these positive areas and got rid of that, right, I would be left with the original shape. Does that make sense? So I'm going to treat all this as positive area, and this is negative area, okay? Now, with that, oh, sorry. Let's put some dimensions on this so that we can have a common frame of reference. Okay. That can. All right. So this dimension here. So this is 120 millimeters. That dimension 60 millimeters, this dimension 80 millimeters. Okay? So that we're all paying attention, for this shape, what is R? We weren't given the radius of that. But you were able to determine it because if this is 120, that's the diameter, it makes the R 60. Everybody okay with that? That this is 60? So far so good? Okay. And I Actually, we were given it. I'm sorry. I didn't even see that. Whoopsie. All right. This right here is R equals 40. Okay. So far, so good? Okay, so let's see what we can do here. All right, so I'm going to set up a table down here. Okay, let's set up a table down here and let's start listing our shapes. So how many shapes do I have? I have 1, 2, 3, 4. Okay, so 1, 2, 3, 4. Okay, and let's name them. So let's call this semicircle. I know that's kind of tiny, my apologies. That's a rectangle. That's a triangle. And that's a circular hole. Okay. All right, so ultimately we're going to have to compute this, right? We're going to have to compute the sum of XA and the sum of the areas, the sum of X times the areas, the sum of Y times the areas. So maybe the first thing that we will do is let's compute the areas first. So the areas are going to be in square millimeters, okay? So let's take the semicircle. How do we compute the area of that semicircle? How do we do that? Pi r squared over 2. So maybe I'll squeak this in here. We'll say pi r squared over 2. Whoop. Oh, pi r squared. Okay. And what does that come out to be? We'll say 2 decimal places. I'm making you break out the Casio FX 115 ES Plus or similar scientific calculator. So we'll say 56, 54, 87. Second. Okay. All right. Let's do the next one, the rectangle. So shape 2 is the rectangle. What's the area of that rectangle? Base times height. So that we'll just call that BH. And I think I could do that one in my head. 9,600. 12 times 8, 96. Add up the zeros. All right, so, and I'm not putting any units here because I put the units up top. So, all right, what about the triangle? What's the area? BH over 2. So that's going to be 120 times 60 over 2. And that's going to be, what is that? 120 over 30, 3,600? Okay. Now what about shape 4? What is the area of shape 4 going to be?
Negative pi r squared.
I love the fact that you said negative, because it's a hole. It is negative pi r squared. And all kind of blend together. So, let's see. I'll go ahead and write this one. I'm getting 5026.55. By the way, this table, we might go all the way over. So I'm going to try for that not to be the case. Okay. So far, so good? Okay. So now what we're going to do is we're going to do the, let's do the X one first. Okay, so let's do the X distances. Okay. So we're going to take each shape one at a time. Okay, so this is what I want to do. Okay, we're looking at the x-axis, not both, just the x-axis. Okay, so I want to say horizontally, the distance is this way. How far is it from the origin to the centroid this way of each individual shape? Okay, so let's take the semicircle. How far is it from here this way to get to the centroid of the semicircle? 60, right? Because we're only talking this way, right? So this is just going to be 60. Okay? What about the rectangle? That's also 60. Okay? What about the triangle? Bless you.
40.
Is it 60? Look right
Is
here.
it 20?
Well, hold on. This is the triangle, right? We're going from here to the centroid, right? Think about where the centroid is, right? Where is the centroid on the semicircle? It's about right there. About right there. Where is it on the triangle? It's over here, right? So, what is it? Is it 60?
Should be 40.
It's 40. Let me lower that down a little bit. And what is it for the circular hole? 60. Right? Because, I mean, the circular hole and the semicircle, like the center of where the radius begins, is all at the same spot, right? Now, are all these distances positive? Yes. They are all positive, right? Because they're all going this way. They're all, here's the origin, going that way. Does that make sense? Okay. So, how do we compute the location? Well, we sum up the areas, but we need to sum up the x times the areas. So we need a new column now, which is x times the areas. Okay? So how do we do this? Just that times that, that times that, that times that, that times that. Just row by row. By the way, what software program will be very nice for this type of calculation?
Excel.
This is an Excel-friendly calculation if I've ever seen one. Okay, I'm going to do these for you because I have the belief that you all can just multiply numbers. So this one is 339,292. I'm just going to even numbers. This one's 576,000. 144,000. Lower that down just a tad. And this one is negative. $3,015,93. That 9's going to make me want to do that better. Okay. So far, so good? Okay. Now, in order to compute the location of the centroid, I need to sum these columns up. So I'm going to put a little summation down here. And okay. All right. So for this column, what I'm going to do is do that, that's negative. I've got to believe you all can add numbers, right? So when you do that, you're going to get 13828, we'll say 0.32. Okay? This column, when you add it up, you get 757, 699. So therefore, the location of the centroid is just that ratio. And when you chug this out, you'll get something like 54, getting ahead of myself, 0.79 millimeters. Now, does that value make sense? I mean, does that feel like that's about where it should be? Sounds about right, doesn't it? Everybody okay with this so far? Okay. Forgive me, I'm going to scroll up a little bit. Okay, we'll do that. All right. Do I need to leave it here for a second? Everybody good? Okay. Now, I want to do the same thing for the y-axis, okay? But you got to pay attention with how you do the y-axis. Or really with any axis, but I like this problem because it does sort of reveal some things. Okay, I'm going to do this in a little bit of a different order, okay, for this reason. Let's start off with the rectangle, okay? For the rectangle, if I go vertically from the origin to the center of the rectangle, how far up am I going to go? That diagram's horrible, by the way. Let me redo that. Because this is supposed to be like that. That was bad. Okay, so if I went from vertically from the origin to the center of the rectangle, how far up am I going to go? 40. Okay. How about for the triangle? This is 60, right? So if this is 60, what's that? So what do I put right here?
Negative 20.
Because you're going down, right? That's exactly right. We're going down, so this is negative 20. Okay. Okay. By the way, let me do something. Let me put something over here. All right, hold on. Okay, let's do something over here. What was the radius of the semicircle, by the way? What was it, 60? 60. What did we say that this formula was, 4r over 3 pi? Let's calculate that. Let's just do this over here on the side. So for the semicircle, what does that equal? 25.46. Do I have a second? Okay. So that goes here, right? Now you're shaking your head no. Why are you shaking your head no? You've got to add the rectangle. So let's go back up to the image, right? Okay. So, scroll up a little bit. so I don't have to reach too far. Okay, so we're trying to get from the origin to here, okay? Now the 4r over 3 pi, all that is this distance, right? So this distance right here, that's 25.46. But that's not, I'm not asking you how far this distance is. I'm asking you how far it is from the origin to that. So it's not 25.46, it's 25.46 plus 80. Does that make sense? So this is going to be 105.46. Does that make sense? That, I'm telling you, that right there is the number one mistake when doing these problems. Right there. Oh, this is 25, so we put 25 on the table. No. All about frame of reference. Okay? It's 25.46 from here, but I'm not asking from here. I'm asking from there. Does that make sense? Okay. So, if that's the case, what do I put for the circular hole? Okay, let's talk about that. So first off, 80 is the right answer, okay? So you said negative, right? We've already accounted for the sign by taking the area as negative. I'm not asking about the area, I'm asking where it is, okay? And the hole is centered right there. This is where the hole is. That's where we drill it, okay? And from the coordinate system going up, this dimension is 80. Okay? Does that make sense? That make sense, everybody? Okay, so okay. So now, here's the thing. Once you figure out this column and this column, the rest is just algorithmic. It's just sort of plug and chug, right? So we're just going to do that times that, that times that, that times that, that times that, sum them up and do the same thing. So this part should be kind of boring. So I'll go ahead and give you some of these values. So this one ends up being 596, 389. This is 384. This is negative 72,000. Why is it negative? Positive area, negative y. And this one's negative because it's, it's negative, sorry. Because it's a negative area, positive y distance. So when we sum this up, we get 506, 265. So uh, 130 in the same area. And this ends up being 36.61. So the question asked, where is the centroid? And I propose to you that the answer is a coordinate. And that coordinate is that. And we're not done because I want you to think about something here in a bit. But take a second. What do y'all think about this? Is this too bad? This is one of the most fundamental calculations in engineering, period. This is one of those things that somebody who's been practicing engineering for 30 years, they can do this in their sleep, right? This is just that fundamental to engineering. You will do this, again, in other classes, guaranteed, guaranteed. So, fortunately, I don't know about you, but I think it's easy, you know? But you will do this again. You will do this in fluids. You will do this in deformables. You will do this in structures and all sorts of things. So, you'll do it again, all right? I promise. Now, I want to show you something to sort of pause and ponder, if you were. But before I move on, any questions? Do I need to stay here for a bit? Okay. Watch this. Here's something to consider. And bear with me. I've got to do some artwork. Okay. Here's this. Let's try this. Let's take this shape and let's subtract the following. Oh, wrong way. So let's take this solid plate and subtract a triangular hole and a circular hole. If we had done the problem this way, do you think we would have gotten a different answer? No, wouldn't matter, because we're ultimately accounting for all of the area. If you really want to get silly with it, here's something else to consider. Let's take this shape. How many shapes did we break this up into? 2? Okay, I'm going to break it up into 7 shapes. I'm going to say, here's this shape. Here's this shape. Let's see. Let's do that. I mean, I'm being silly, but I'm saying, like, what if we said, okay, we have a quarter circle, a rectangle, a square, another square, and then 2 triangles, along with these 2 holes? Would we have gotten a different answer? No, we wouldn't have. We would have gotten the same answer. This would have been more of a pain, but we would have arrived at the same centroid location, right? Because we're doing it the same way, okay? The point I'm making is I want you to sort of think, there's more than one way to do these problems, and there's no right or wrong way, okay? So I don't want you to get worried that, you know, if you're doing an exam problem or, you know, you're looking at a problem a different way than maybe one of your friends, you might get the same answer. That's okay. You see what I mean? So you can have fun with this. Okay, sound good? All right, giving you 4 minutes of your life back. So what we're gonna do, by the way, in our next lectures, is we're gonna look at, here's the centroid of an area. We're gonna look at things like, what about the centroid of a volume, or the centroid of a series of lines and whatnot. So we're gonna add that, we're gonna extend this. Okay, that's all I got, everybody. I'll see you.